So again, thank you. I appreciate the opportunity to talk with you about advancing scientific computing with today's quantum computers. This is work that is intended to introduce the idea that we can use quantum computers that are being built today to start performing scientific calculations. And I think that is something that will be of interest to this conference, because this may offer a new way of doing computational simulations and understanding different ways of how to simulate modeling and simulation of physical systems. And as Lev was saying, this is exactly the topic that we're interested in at Oak Ridge National Laboratory. And I'd like to explain first why we're interested in them. Oak Ridge National Laboratory is a Department of Energy research technology organization located in Tennessee. You can see in the picture here, it's a very large facility, and it consists of many different types of experiments. One of the most important experiments at the facility are done at the spallation neutron source, which is the world's brightest source of neutrons. This facility is used for characterizing materials by using neutron spectroscopy. And of course, Oak Ridge has a long history of developing and synthesizing new types of materials. However, in order to understand those measurements, we use modeling and simulation as an important part of that theory. And we have at Oak Ridge, the Oak Ridge Leadership Computing Facility, which houses some of the world's fastest supercomputers. And as was noted in the previous talk, it's where the Summit supercomputer is currently located. These modern high-performance computing systems have demonstrated a steady progression of increase in performance over the last decade. At Oak Ridge, we started with the Titan supercomputer, which was a massively parallel system that first began to use GPUs as computational accelerators. We're currently using the Summit supercomputer, which again uses GPUs to offload scientific calculations and accelerate the workflow, especially matrix vector multiplications and other linear algebra operations. We are planning on the Frontier computing system probably later next year to also follow a similar architectural design, CPU-based nodes that have GPUs attached to them. This type of massively parallel performance enables us to perform scientific calculations much more quickly, but it's not yet clear what is beyond Frontier in terms of architectural design. For that reason, we're beginning to evaluate different technologies like quantum computing as an alternative approach to accelerating scientific workflows. When we look at the types of scientific computing applications that are run on these supercomputers, we see that many of them actually make use of quantum mechanics. Material science, physics, including astrophysics, biology, chemistry, earth science, many of these application domains implicitly and explicitly use quantum mechanical models to derive their forecast and expectations. So the question becomes, what type of future computing system might be able to accelerate these types of scientific applications? Now, it was nearly 20 years ago that, nearly 40 years ago, that Richard Feynman made the point that you see here. If you want to make a simulation of nature, you'd better make it quantum mechanical. And this, of course, is one of the motivations for pursuing quantum computing, that by controlling individual quantum mechanics, we'll be able to emulate those effects and therefore simulate those systems using quantum computers. But Feynman goes on to make an equally important point. By golly, it's a wonderful problem because it doesn't look so easy. And this is perhaps where we are today, trying to get to the point where we can control quantum mechanics in a way that allows us to perform computation. And Feynman was certainly right about both points, the second one being that it doesn't look so easy. So what is quantum computing? I'll offer a simple introduction for the purposes of this talk. Fundamentally, it's quantum mechanical computation. Of course, as the audience will know, quantum mechanics uses a wave function to describe all knowledge about the system. As a fundamental model, it's very different from tracking particle trajectories, such as position and momentum, because the wave function represents a distribution of probabilities that characterize the likelihood of the particle being at any given location in momentum. As an example of this, you can see in the picture of the hydrogen atom that many people are taught first that the proton and the electron orbit each other in some sort of solar system model. However, the truth is shown in the figure at the bottom. This is an experimental image of what a hydrogen atom looks like, plotting the distribution of the electron orbiting the nuclei in the center. This distribution is more correctly described by the wave function that gives rise to quantum mechanics. Now, quantum computing manipulates this wave function in order to perform calculations. This is fundamentally dynamical control of the Hamiltonian that is given in terms of the time-dependent Schrödinger equation. Shown here at the bottom, you can see that the wave function psi of t evolves in time according to the Hamiltonian h of t. While the equation itself is specified by the physics of the universe, humans have the ability to interact with this equation through the Hamiltonian by designing control fields that permit us to actually manipulate the dynamics of the wave function. This is going to be the basis for performing quantum computing, to use control of the Hamiltonian and the Schrödinger equation to drive the wave function towards a desired outcome. Now, David DiVincenzo has laid out several basic requirements that a quantum computer must demonstrate in order to perform these types of computations. The first is it must be able to encode information in a quantum mechanical state. In this example, we're going to talk about qubits. Qubits are the quantum analogy of a bit. They represent a superposition of two logical values, which we'll call 0 and 1. We can visualize them on the Bloch sphere as the north and south poles, and we can represent a qubit as any point on the surface of that sphere. Unlike a binary logical value, which can either be 0 or 1, a qubit, of course, can be a superposition of these two values. Moreover, there is an infinite number of qubit values. This is very different from the two values that a binary bit can take. So a qubit is the fundamental piece of encoding information for a quantum computer. And we need a scalable system of qubits in order to build a quantum computer that can represent arbitrary sources of information. Now, in addition, we have to be able to manipulate those qubits. That is, we have to be able to first initialize them into a well-known state, a fiducial state. For the simplest example, we'll assume that's setting the qubit's value to 0. We must be able to set all the qubit values to 0 and then perform a universal set of quantum gates on them. Quantum gates correspond to the logical operations that enable us to implement computation. We'll talk in a second about the different types of logical operations and their models that can be chosen here. Decoherence, though, is a factor that affects all physical systems of quantum computing. It's the loss of information due to interactions with the surrounding environment. In order to build a quantum computer that performs useful calculations, we must be able to perform many gate operations before decoherence has erased the information. So our decoherence times must be much longer than our gate operation times. Finally, in order to retrieve information from a quantum computer, we have to be able to measure the qubits. Of course, the measurement process is a projective operation that casts the qubit into a specific logical value, that is either 0 or 1. However, the probability with which we observe that value will be determined by the sequence of operations that are performed prior to measurement. This is how quantum computation enables us to arrive at a desired outcome. By manipulating the wave function through the application of quantum gates, we're able to perform a calculation and then observe that result using measurement. The principles of operation for a quantum computer therefore begin with preparing the quantum wave function psi at time 0, t0, in this fiducial state. We'll set that equal to the 0 state. We then apply a sequence of unitary operators or gates that correspond to the dynamical evolution of the quantum system. Again, this is through manipulation of the Hamiltonian h of t. At some time in the future, t1, we have prepared the quantum state psi in a superposition of 0 and 1. We can then measure that quantum state, and we will observe 0 with a probability given by a squared, magnitude of a squared, and 1 with a probability given by magnitude of b squared. Now, I've given this example using a single qubit, but of course, multiple qubits can be used in the description of the quantum state. And this is what gives rise to the representation of information using the wave function. How we apply these operations, though, is a choice that depends on the computational model. One of the most popular choices is the circuit or gate model, in which the time evolution of the Hamiltonian is binned into discrete pulses. This allows us to isolate individual logic operations and then compose them together to represent a quantum program. By contrast, an adiabatic model uses a slow, continuous time evolution of the quantum state to drive towards a target quantum state. This is a pictorial example of how we represent quantum computing using gate operations. You read this diagram starting on the left, where we specify the register, here 5 qubits, the 4 of them starting off in 0, and the 5th in an arbitrary state psi. And then as we move to the right, we apply individual gate operations represented by boxes and letters that perform Hamiltonian evolution of the quantum state. Finally, on the far right-hand side, we perform measurement, which projects those quantum systems into a specific logical value that corresponds to the outcome of the computation. Now today, we have access to current quantum processing units which realize the basic principles of a quantum computer. These QPUs are designed using many different types of technologies. On the right, you'll see examples of the types of technologies that are currently being used for quantum processing units. This includes superconducting electronics, as well as photonics and trapped ion technologies. Each of these technologies offers different challenges for the control of Hamiltonian evolution. They are all maturing technologies that have been able to demonstrate relatively small register sizes, up to 65 qubits, that have very high 1-qubit gate fidelities, but only modest 2-qubit gate fidelities. These gates are the important part that allow us to entangle qubits together and prepare superpositions across multipartite systems. In addition, the current quantum processing units are limited in their connectivity. However, they have good addressability. This means that we can program these systems to act on specific registers, but the number of operations that are able to be applied are limited by both the noise and the constraints of those connections. Because of these limitations, current applications of quantum processing units are limited. And so we begin to enter into a new era of quantum computing where we start to understand how constraints on quantum processors become an important part of their utility. Many vendors are offering access to these early processors, including D-Wave, IBM, IonQ, Google, Rigetti, and Alibaba. However, in all examples, these represent a client-server interaction or a cloud model of quantum computing, in which a user accesses this experimental processor through a web server, issues a program that is then run remotely on that processor before retrieving a result. Remember, we're motivated by the idea that high-performance quantum computing may need new architecture choices in the future. This current interaction model is very loose integration with modern computing, and therefore we anticipate that we're a long way from being able to use these systems in high-performance computing systems. I'd like to give you a few examples of how quantum processing units are currently put together. The first is an example of the IBM Q processor, which is a programmable integrated superconducting electronic QPU. You can see in the figure on the right an example of a 16-qubit transmon device in which it has been electromagnetically shielded, pumped down to an ultra-high vacuum, and then cryogenically cooled to 13 millikelvin. This very low temperature is necessary in order to capture individual electrons or Cooper pairs and prepare a superposition of those electronic states to represent the zeros and ones. IBM has developed devices up to 65 qubits that are general purpose gate model devices. This means that we can use sequences of operations to program these devices and perform arbitrary calculations. The errors in those gates have been measured down to less than 1%, while the measurement errors, which are responsible for generating classical output, are on the order of 5%. Again, it's a cloud-based access, and it does use some sort of authentication and management system to enable people to access that device. Here's an example of the coax cables that are necessary to program the processor itself. Those are then housed inside of a dilution refrigerator like the one shown here. The cylinder in the center of the picture protects the device and the coax cables, while the surrounding equipment is responsible for controlling the thermodynamics of that system. This includes the temperature and the pressure, as well as the electromagnetic fields that are driven into the device itself to control its Hamiltonian evolution. A second example is given by the D-Wave quantum computer. This is also based on superconducting electronics, but now it uses an adiabatic model of computation. It's again pumped down to very low vacuum and cryogenically cooled to 13 millikelvin. In the picture, you can see the electromagnetic shielding that prevents interference from radio frequencies with the operation of the device. D-Wave has fabricated a 2048 qubit chip, and they've also recently announced a 5,000 qubit chip. In both cases, these devices are special purpose. They're intended to solve optimization problems by finding the lowest energy ground state of a Hamiltonian. Again, it's based on remote access using authentication to program those devices and return results. This is the interior of the big black box, which represents the cryostat that's used to cool down the processor. The processor itself is located in the housing at the bottom of the cryostat, while the individual stages represent transitions in the temperature that is used to cool down the control electronics. This is an example of the device itself, where you see the pins coming into the chip located here that is again based on superconducting Josephson junctions in order to form the qubits, which are based on magnetic flux. Now at Oak Ridge, we've begun the process of analyzing these different processors in order to understand their readiness for performing scientific calculation. We monitor the DiVincenzo criteria that I talked about before, the scale of the qubits, the ability to initialize them, the fidelity of the individual gates, a parameter we call duty cycle, which is the ratio of gate operation time to decoherence time, as well as the measurement fidelity. There are some additional criteria related to the movement of qubits that come into play when considering different technologies. While all of these examples are very impressive, none of them yet quite reach the expectations needed to achieve the vision of fault-tolerant quantum computing. Fault-tolerant quantum computing is the idea that a quantum computer will always incur some type of error, either due to decoherence and interactions with the environment or imperfections in the operations of those gates. This therefore uses redundant encoding of information to mitigate the entropy that these errors cause in the storage of information. However, fault-tolerant operation requires many more qubits at a much higher quality than is currently available. Therefore, we're not able to perform many of the ideas that Feynman originally proposed using current devices. Instead, we find ourselves looking at what's called noisy intermediate scale quantum computing, or NISQ computing. In the NISQ regime, noise and errors are still limiting factors in quantum computing performance. there are too few qubits to perform error correction and too much noise to ensure stability. This again limits the depth of the algorithms that we can implement using sequences of operations. That depth means that there are relatively few gates, and it's also static, which means that there's little opportunity to modify the program in the presence of errors. However, we have access to these systems now, such as the IBM and Rigetti devices shown here, that we can begin to use for testing ideas of how quantum computing can apply to scientific computing. There are many examples of how scientific computing can be performed using quantum computers, including quantum simulation, calculating partition functions, discrete optimization, and machine learning, among many others. For the Department of Energy and Oak Ridge National Laboratory, these ideas directly relate back to our scientific domains: high energy physics, material science, chemistry, biological systems, as well as others. However, in the NISQ regime, it's not yet clear when these particular algorithms will make an impact on the individual scientific areas. Therefore, we find ourselves largely playing with toy models and trying to understand the behavior of these algorithms in the presence of noise. I'd like to focus on the example of quantum simulation. There are, in fact, two approaches to this particular algorithm. The first, based on a digital approach, decomposes the time propagation operator, e to the minus iht, into a sequence of individual time propagations over shorter times, what's traditionally known as trotterization. Now, trotterization can equally apply in a quantum computer, in which I perform evolution of the Schrödinger equation over short windows of time by controlling the individual Hamiltonian. In the example of a time-independent Hamiltonian, I'm given an expression such as the Heisenberg model shown here, where I need to now decompose that Hamiltonian into individual gate operations. In particular, because of limits on the controllability of the qubits themselves, I have to decompose my time evolution operator into 1 and 2 qubit operations. So you can see in this example circuit at the bottom from Lucas Lamada and co-workers of how this particular Hamiltonian acting on 3 qubits can be decomposed into a sequence of operations. However, you'll note that the sequence of operations is much longer than a single impulse propagator of the Hamiltonian. And this is where the depth of the quantum circuit becomes an important factor in our ability to test these ideas. The other approach to simulation uses analog simulation, in which the physical Hamiltonian of the system that's being controlled is driven to match a target Hamiltonian of a desired molecule. Here, there is a unitary operator U that I wish to simulate acting on a quantum state psi 0. However, in order to perform that transformation, I'm going to control the physical Hamiltonian of the device to mimic the map under the action of U. This means that I now have a mini-body Hamiltonian, such as the example shown at the bottom, in which I'm controlling the external electromagnetic fields that drive the interactions of that Hamiltonian. This idea of analog quantum simulation offers the opportunity to address directly many-body physics, but it opens up a very complicated control problem in identifying the control fields that actually affect these maps. As an example of digital quantum simulation, I'd like to talk about performing computational chemistry using quantum computers. In the NISQ regime, there is an algorithm developed around the variational principle in which we search for a quantum state that minimizes the energy defined by a Hamiltonian. In this case, the Hamiltonian represents the objective function of the minimization, and the quantum state represents our ansatz for what may be a possible solution to the ground state of the Hamiltonian. By searching through the parameterization of the ansatz, we can attempt to find the quantum state that minimizes the energy of the cost function, in this case, the Hamiltonian. The variational principle guarantees that the quantum state that minimizes the energy must therefore be the ground state. However, our ability to find that ground state depends on two factors. The first is the proper choice of an ansatz Hamiltonian, psi, that depends on a set of parameters, theta. The second is the identification of the parameters theta that minimize the energy and therefore represent the true quantum state. In practice, this is performed using a search routine in which the quantum system is initialized into the all-zero state. The sequence of operators necessary to perform that, to prepare that quantum state in the given ansatz state are applied. And then the Hamiltonian, or cost function, is estimated by measuring the action of that Hamiltonian on the quantum state. I estimate the energy for the given quantum state that's been prepared, and if it satisfies my convergence criteria, then I finish my calculation, and I report both the quantum state and the energy that was observed. But if my convergence criterion is not satisfied, I then change the parameters in my state preparation and repeat the process. This process can continue for quite some time, depending on the landscape in which encodes the quantum state and the energy surface. However, it has been applied successfully to finding the ground state energy of small diatomic molecules. This was first demonstrated in 2017 from a team at IBM, in which they looked at 3 small diatomics, H2, lithium hydride, and beryllium hydride. And in this example, you can see that the black dots represent experimental results using the IBM processor to calculate the ground state energy using the variational eigensolver method. The red lines denote the exact, the dashed lines denote the exact energy surfaces, while the blurry lines represent the outcomes expected from numerical calculations. You'll notice for hydrogen that there's relatively good agreement between the theoretical lines and the experimental results. This was a 2-qubit problem that was relatively simple to program and used very short depth circuits to calculate the energy. As we move over to the other 2 examples, you'll notice lithium hydride and beryllium hydride deviate from their theoretical results. However, they agree reasonably well with the numerical simulations expected from the quantum computer. It turns out in this example, the lithium hydride and beryllium hydride computational results used a much larger basis set than were available to the quantum computer. And the reason for this is that the quantum computer had limited connectivity between the individual qubits that prohibited it from using a larger basis set in its description of these 2 molecules. So the deviations that we see in these examples actually correspond to a conventional problem, which is not using a sufficiently large basis set for the calculation. However, it's a problem that's going to require additional advances in the quantum processor before it can be addressed. At Oak Ridge, we have also focused on quantum chemistry as a benchmark for these near-term quantum computers. In particular, we have applied the variational quantum eigensolver method to a suite of different molecules and techniques for estimating the ground state energy. As you can see in the table on the right, we have looked at additional molecules, including sodium hydride, potassium hydride, and rubidium hydride, using a family of different ansatz. 2 examples are shown on the left in the terms of these quantum circuits, and then also additional methods for trying to mitigate against the noise that is expected by running on these NISQ devices. Our examples find that we can do relatively good for certain combinations of these choices for the algorithm. However, there is always a floor to the amount of noise that's present in the processor that limits the accuracy with which we can achieve these results. In this example, you see plots on the right-hand side of estimating the ground state energy of the sodium hydride molecule using both the IBM and Rigetti processors. The x-axis represents the single parameter theta that parameterized the ansatz, and we've scanned through this parameter to find its minimum. We've set that to the value 0, and we've identified the dip where we expect to find the lowest energy for that molecule. When we run this calculation on the IBM quantum computer, we obtain the raw red circles, or sorry, triangles that represent the outcomes of those measurements. However, by performing these error mitigation techniques, we can remove some of that noise and get down to a much better solution for the relative to the theoretical estimate. A similar calculation was performed on the Rigetti processor, another superconducting electronic QPU, and we again see very similar results. There is a relatively high noise floor in the raw data that can be removed by using error mitigation techniques. For more details on how these are implemented, I'll refer you to our software package called XACC, which is available online and provides the explicit codes that are used for running these calculations on the IBM and Rigetti processors. And we've also talked about this recently in a publication in MPJ Quantum Information. I'd like to next transition to a demonstration of how analog quantum simulation can be used for scientific computing. This example focused on material science calculation. In particular, calculating the phase diagram of a many-body system is a complex and challenging problem. As we heard in the earlier talk this morning, looking for these quantum phase transitions is especially interesting because entanglement appears, and that can, again, place challenges on numerical calculations that need to monitor those quantum states. Our interest is in understanding whether or not quantum computers can be applied to this problem as well, because as a quantum computer naturally represents a quantum state, it may be able to provide a new approach to calculating these types of simulations. Our particular example is going to look at a fractional magnetization plateau, such as the ones that are found in the rare earth tetraborides. This is an example of holmium tetraboride, which, as we scan through the longitudinal magnetic field, demonstrates a change in its magnetization that starts off at 0 before transitioning to a 1/3 plateau, and then also demonstrating other plateaus before becoming saturated at high magnetic fields. It has been proposed previously by Shasterly and Sutherland that this type of fractional magnetization may be due to a frustrated Ising model that describes the underlying spin system. In the Shasterly-Sutherland Ising model, we use the lattice shown here, in which the square grid represents the J1 interactions between two spin sites, while the diagonal red dashed interactions represented by J2 occur in these alternating patterns. Now, the presence of these triangles within this particular lattice are believed to give rise to a very complex phase diagram, in particular a 1/3 magnetization plateau in which the spins are either 2 paralleled against 1 anti-paralleled or vice versa. Now, of course, there are other phases in this diagram as well, depending on the relative values of J1, J2, and the applied longitudinal field. Our question using analog simulation was whether or not we would be able to simulate these behaviors. I'll give you the answer first, that we were able to simulate, and this is the phase diagram that resulted from that particular calculation. I'll now walk you through a few of the details of how we did that. First, we're using the D-Wave quantum computer, which again is based on an adiabatic model for controlling the ground state dynamics of magnetic qubits known as flux qubits. We drive the dynamics of that system using the Schrödinger equation and the time-dependent Hamiltonian. By initializing the flux, the adiabatic condition therefore confirms that if we change the Hamiltonian sufficiently slowly, we will stay within its ground state. And therefore we can drive it towards a given phase of the Ising Hamiltonian that we saw previously. Now, the D-Wave processor, though, has a limited connectivity that we need to work with. This is an example on the right of the 4x4 chimera lattice in which we're going to embed this problem. The operation, again, begins by starting off at a relatively low value of the applied field. You can see the Hamiltonians up here. And then changing through that, controlling that evolution of that schedule in order to drive the initial Hamiltonian towards a final Hamiltonian given by the icing model. In pictures terms, what we've done is we've created a relatively flat energy landscape that begins to distort as we change the Hamiltonian before a global minimum is generated, and that traps the quantum state in the desired configuration. Now, our embedding of this Hamiltonian into the processor lattice required a mapping of the logical interactions. So here are those dashed and solid lines representing J1 and J2. And then this is an example of how those configurations can be embedded directly into the D-Wave processor. After performing that procedure, we are able to embed 500 spins on the 2000 qubit system, but I'll call out there are several defects due to imperfections in the device. Running the forward annealing diagram generates an ensemble of measurements that correspond to the spin configurations of the qubits. Here, black represents spin up and red represents spin down. You can see that there's a rather complicated network of or interaction pattern here, and we want to be able to evaluate how good that represents the true system by calculating its static structure factor, which is effectively the Fourier transform of the spin-spin correlation. Looking at that particular diagram, we see that as we change the longitudinal field, the magnetization of the system does increase and appears to almost plateau before continuing off to saturate. However, when we compare these results to the exact quantum Monte Carlo configurations, we find that there's relatively poor agreement in the plateau regime. In particular, the slope remains too steep. When we look at the analysis of the static structure factor, we can actually see that the peaks, which we expect to show up in this plateau region, are slightly distorted and not of equal amplitude. And so this indicates that we may be having some problems in our simulation that are giving rise to these defects. We believe that the reason for this was due to the boundary conditions that came from the defects within the embedding, and then of course the edges due to the finite size. I've highlighted those defects here in terms of the blue dots, and we developed a strategy to mitigate against them by changing the individual biases applied on these edges in order to achieve a mean field boundary condition. In particular, what we do is we identify those spins that are on the edges as blue and those inside the bulk as red. We then minimize the field that's applied only on the edges to ensure that the deviation between the magnetizations is as small as possible. This allows us independent tunability of the reason we're able to do this is because of independent tunability of the biases in the physical processor. Finally, we also used a new method called reverse annealing, in which we prepare our quantum system in what we believe may be a good initial state for the solution, and then anneal in the reverse direction, essentially performing a mixing operation, before then annealing in the forward direction, which again attempts to create a global minimum to trap the ideal probability configuration. We repeat that process in impulses over a number of different samples, and then towards the end of that process, we perform our measurements to collect out the best approximation to the ground state. Now we find an ensemble of different results for the particular parameters of the Shasterly-Sutherland icing model. Here is the longitudinal field applied H, and here's the ratio of J1 to J2. We again see the 4 distinct regions that were expected from the theoretical diagram, And when we look in each of these regions, we observe spin configurations that represent the expected behavior. In particular, when we look into the fourth region, which is the frustrated fractional magnetization plateau, we see the 2-to-1 frustration between the spins, either both parallel, one anti-parallel, or vice versa. Now, repeating the static structure magnetization result calculation, we find that again, the plateau is much flatter due to our corrections in the boundary conditions, and that the peaks of the static structure factor in this region are also much brighter and more symmetrically distributed. These results indicate that the improvements to our simulation from using the open boundary condition modification and the quantum evolution Monte Carlo technique have contributed to this. Our next steps are to perform experimental validation of these ideas, in which we attempt to calculate the static structure factor directly from experiment and validate those measurements against our quantum computations. So let me conclude. I've shown today how quantum simulation may enable scientific computing with today's QPUs. We looked at two examples, chemistry and material science, using the methods of digital and analog quantum simulation. I think that these are interesting examples that offer new paradigms for scientific computing and also crosses the barrier between what looks like computing versus experimental physics. In my opinion, NISQ devices are a good opportunity to test ideas and validate what could be future quantum computing workflows. However, there's a lot of knowledge that's currently required to make those intersections happen. You need to understand both quantum computing, like the variational quantum eigensolver, as well as the domain, like chemistry or material science, in order to make success. However, it's very early days in this field, and I'm looking forward to continuing to explore this research in the future. With that, let me show you a picture of all the many people who have contributed to this research, and thank you for your time and the opportunity to speak to you today.